Good day and welcome to this fourth video in this short series on approaches to optimization of treatment selection on infrastructure deterioration models. So in the first video in this series I explained the nature of this problem and walked through the concept of a Pareto front with concave and convex areas, and I also explained the essential elements of this type of optimization problem. So please go back to the first video and have a look at that so that I don't have to explain that again in this video. What I want to do in this video is just briefly recap on what we found in the first three videos. So we basically looked at three different approaches for this optimization problem. We explained the structure of the problem. We've got four different network elements, A, B, C, D and E, sorry, 5 elements, A, B, C, D and E, and for each we've got several candidate projects, and we showed that there are three different approaches that we've explained, at least in this video series, dealing with which we call bottom-up greedy, bottom-up egalitarian, and bottom-up decreasing I incremental benefit cost ratio. And we showed that for this toy problem with just 5 network elements, all three approaches gave the same result. But we also showed in the third video that if you've got many more elements on your network, that you can actually get different results with all three of these approaches. What I want to do in this video is just to highlight for you that even with the small toy problems like this one, we can actually find some solutions that are better than the preceding three methods that we've tried. And that I'm going to illustrate by looking at the NL-OptiTR framework, which is an optimization framework that you can use in R. And I'm going to specifically look at this framework called the Improved Stochastic Ranking Evolution Strategy algorithm that is available in this toolbox. So I'm going to just switch to RStudio. Don't worry if you don't know how to use R or RStudio. I just want to illustrate for you how we actually run this problem. So here I've got an R script which I've just put together to read the problem structure that we've defined in our toy problem, and that's the same structure that we used in the first three videos. And I've basically written here an objective function which will calculate the total benefit for a given set of project options and return that benefit to our optimization problem over here. So that's just, as you can see, it's not a very complex little function that I've written here. And here I am using the NL-OptiTR framework. I'm using that Improved Stochastic Ranking Evolution Strategy framework to calculate the objective and to try and find the optimal solution. So I'm going to run this, and it's going to run for a while, and then we will look at the outcome from this algorithm. So remember, this is a very small toy problem. We've got only 5 elements, a network consisting of 5 elements. So it's a very small problem, and let's see how this algorithm does. So here I'm running the algorithm. You can see here at the bottom, the algorithm is going, it's now at 2,000, 3,000 iterations, and it will run like this for a while. All the time it's trying different strategies for each of those 5 elements and seeing if there's a combination that gives a better benefit than all of the others. All right, there it's now happy that it's converged. And if I look at the outcome here, you can see I've got 5 elements, A, B, C, D and E. And for the first one it picked the project 5, for the second one 3, for the third one 3, and then 2 and 4 for the last 2 elements. So let's go back and put that in our spreadsheet and see what the benefit and the cost is for this solution. So here I'm back in my spreadsheet, and what I've done here at the bottom, this is just the same outcomes that I got from the other 3 algorithms as we explained in video 1. And you can see that this is basically the solution that we discussed in the first 3 videos. We got an overall benefit of 552 for a spending of $56. Compared to our budget of 67. Now with this framework, with this optimization framework, if I put in the projects, these projects over here that our algorithm has selected as the optimal ones, if I put those project numbers into my solution matrix here, you can see that I'm getting now a benefit of 566 for a spending of $65 out of a budget of 67. And so here I've got a benefit that is higher, 556 compared to 552, than any of the other three algorithms that we tried in the first three videos. And what that shows you is just that how complex this problem is, because we've got three different heuristic approaches that give a very fast solution. But if we try to use something that is a bit more sophisticated to try and solve this, we can actually get a more optimal solution. One thing to consider is that although this is more optimal, this ISRES algorithm gets a better benefit, 566 compared to 552, it does that for quite a high increase in the spending. So although the spending is still within my budget limits, I am almost going about 20% higher in the spending for very little increase in benefit. So you may want to argue that this is still a better solution in an engineering sense, but if you are talking about true optimization, clearly there are different approaches that can do better than these three heuristic approaches that we have explained in the earlier videos. So I just want to highlight that by no means the three algorithms that we explained in videos 1 to 3 is the end of the line in terms of how you can approach this problem. And indeed, at Lonrix, we are continually pushing forward and trying new algorithms to find if we can get ever closer to an absolute optimal solution. However, as you noted when I ran that script in R, even for this small toy problem, it took quite a while to get a solution. If we are looking at hundreds or thousands of network elements, that type of approach rapidly becomes impractical. And in fact, in our experience, the evolutionary search type of approaches don't always find even close to an optimal solution as you would get with these other more practical approaches. So that's just something to consider, and I hope that is useful to you. Thanks for watching.